Remember that it's important that the Noether procedure involves the equations of motion, because we want to say that something is conserved not in a trivial mathematical identity sense, but rather there's some content, there's some physical content in what we're saying. And the physical content is in fact coming from the equations obeyed by the vector potential. So the first faculty is that the transformation properties of A should depend on the choice of gauge. So for example, sometimes there's something called a Coulomb gauge, and a Coulomb gauge is not relativistic covariant. So you shouldn't be surprised that if you choose a Coulomb gauge, the transformation properties will be different from if you choose the Lorentz gauge, which is what we'll do in fact. So because we want to impose, because we want to study space-time symmetries, we will choose the Lorentz gauge because it is Lorentz invariant, and because it's Lorentz invariant, the solution of A with the Lorentz gauge would be Lorentz covariant. Right. So A. So with this choice, then we can think of A as Lorentz vector. Or just Lorentz covariant. Okay? Meaning it just transforms properly under Lorentz transformation. Otherwise, it's not true. Right? So if you do it for example, in the Coulomb gauge, you shouldn't expect that it is in fact covariant. Not sure why the book doesn't explain it this way, but if you want to be very, very careful, it's actually a homework problem in testing Schroeder, but I decided to do it because I think the book doesn't explain it properly, apparently. And furthermore, now we can study, what the transformation properties are. Okay? So, actually, there's a cheat that we can use, but I think I'll do it because I'm assuming that it's not completely familiar with you guys. Right? So x mu is going to go to x mu plus a mu. Let's do that first. Okay. And so dx mu will go to dx mu. And so therefore a mu. So even though a mu is a Lorentz tensor, the d doesn't transform. So this will go to a mu of x plus a dx mu. And for small a, you can now Taylor expand. This will be a of x plus a sigma d sigma of a mu of x dx mu. And now we can ask the question: how does the Lagrangian transform? So again, the Lagrangian is a scalar, as you can see. And so therefore L will go to L of x plus a, which again means it's L plus a sigma d sigma L plus higher order terms. Okay, and this also plus higher order terms. And so that's just a variation of the Lagrangian from Taylor expansion. But if we now calculate the variation of the Lagrangian from varying the fields, what you can recognize is that, of course, it's just quadratic in F, so, which depends on the derivatives of A. So there's only the variation in the derivatives, and there won't be any derivative variation in the field itself. Right? So this is the only term that we need to calculate. But like I said over here, because it only depends on space, it only depends on translations, the derivative of A does not pick up a Jacobian because A is constant. Right? So this will go like A mu x by A because A is constant. There's no Jacobian. If A were to depend on x, which is what happens in curved space-time, then the derivative will also pick up a Jacobian. But thankfully, we don't have to worry about that. So this will just be basically the derivative at x plus the Taylor expansion of the derivative, again at x. And so basically this will follow from this. And as a result, when we do delta, this is in fact delta of partial mu and nu. And now we can plug it in. This gives us A sigma dl d partial mu A nu, and then you get d sigma partial mu A nu. Let's do this calculation and see what we get. So you get A sigma, and then you get a derivative acting on the quadratic in F expression. So, but because it's symmetric, right, I can write this as F, and contracted with metrics. And so this is symmetric. So the first thing I notice is that all I need to do is just differentiate one guy, and let me call that alpha beta. And then I will just contract the derivative of this with alpha beta divided by minus 2, right? Because it's minus 4, but it's symmetric. So once I differentiate it, it will be minus 2 because it's symmetric. And then contracted with d sigma d mu A nu. Okay? But what is d f alpha beta? D mu A nu. This is d of f alpha. Sorry, it's better to use both indices down, and this is both up. So what do we have here? We have d alpha A beta minus d beta A alpha with respect to d mu A nu. What this just means is that if the indices are not the same, you don't regard that as the same variable. If they're the same, it gives you 1. So it just gives you Kronecker mu, Kronecker alpha mu, Kronecker beta nu, minus Kronecker mu, Kronecker nu, beta alpha. Okay, because I swapped the beta alpha. So what that means is I'm going to contract this guys with this guy after just a bunch of Kronecker deltas contracted with f alpha beta. But what is that? F alpha beta itself is an anti-symmetric object. So when I contract this guy with this first guy, I get f mu nu. When I contract this guy with this guy, I get f nu mu. But f mu nu is equal to minus f mu nu. So the minus sign will cancel this minus sign. So I get twice, which exactly cancels the 2 here. So this will leave you with minus A sigma F mu nu, and then D sigma F, D mu A nu. Okay? So this is delta L from varying the arrangement, from varying the fields. And now we can, now I'll show you what the books do. And I'll show you, then I'll show you my way. Okay? So let's do it by the book. Right? So let me just say many books do this, okay? Which is the following. Well, you have this derivative, so I'm going to integrate by parts. So I'm going to first write down minus A sigma partial mu F mu nu, and then D sigma A nu. Okay? But of course, what I need to do is I need to add partial mu on A sigma F mu nu, and then D sigma A nu. Right? So this acting on this will cancel that, and then this acting on A will give me back this term here. I'm sorry, this is a plus and a minus. Yeah? So this acting on this will give me back here with the right sign, and then the plus will cancel this minus here. But this is where the equations of motion come in. Remember that in free photons, meaning there's no current around, then Maxwell's equations are very simple. It's just the divergence of F is 0, which means that this guy is 0. Okay? So what I have is delta L, after I've used the free Maxwell's equation, looks like the following. And then I have my delta L from Taylor expansion, so therefore they must be equal. So minus divergence of A sigma, let me put the minus sign inside, minus A sigma F mu nu D sigma A nu must be equals to delta L from Taylor expansion, and this we have done before, so I'm just going to write it as a partial mu A sigma Kronecker sigma mu L. Okay, and this is because when I take the partial derivative, A is a constant, so it passes through, and this just becomes partial sigma, which is exactly this guy over here. So this is a total divergence. That's a total divergence. I can now combine them and recognize that this is again a local current J mu sigma equals to 0. What is J mu sigma? J mu sigma is F minus F mu nu partial sigma A nu minus this guy, but what is this guy? It's just minus 1/4, so it's plus. There's a minus when you move it over here, but there's a minus in that guy, so it's more minus plus 1/4 Kronecker mu sigma F squared. F alpha beta, F alpha beta. Okay? So again, those of you who have done GR before would recognize that this is not the stress tensor. There are two problems, at least two problems with it. One is that it is not symmetric. So just to make it more clear, I'll raise the index mu sigma. Sigma. This will become eta mu sigma. So this is symmetric, but this is not symmetric. This is an F, this is a derivative of A. That term, this term contracted with this term is necessarily 0 again, because it's anti-symmetric. So I can ignore this term. And you can see that this total divergence is in fact equals to the original term. So I can now put an equal sign. So why am I saying that all this? This is delta. This is delta L. Why do I keep making mistakes? I mean L. And I mean L here. And I mean L here. It's a scalar, so it doesn't matter. It doesn't matter what scalar it is, but it's a scalar. So therefore, delta L here must be equal to this delta L, except that on the left-hand side, on this side, we have used the equations of motion, whereas here we didn't use the equations of motion. Right? But that gives us the following identity. It tells you that this is equals to, let's drop the omega, so it will be minus I, and then it will be the total divergence of what? Of in fact, J hat mu, and then alpha beta, and then it will be x beta, eta alpha lambda acting on the Lagrangian. Okay? And now I can move this onto this side, and we can infer what is the Noether current. In fact, let me just do it directly. So I will erase this equality. This was a minus, so it will become a plus. It will become a plus I omega I, and then I will move my curly bracket over here, and this is in fact 0. So the divergence of the whole thing is now in fact 0. And now I'm going to use the fact that this is anti-symmetric. Minus I J hat mu, again, let's say sigma rho, remember is Kronecker mu, sigma rho minus mu rho sigma. And so what you realize is that this combination is nothing but the anti-symmetric orbital angular momentum x mu partial mu minus x mu partial mu. Okay, and let's write it down. So we have d lambda dl d lambda phi, and then x mu partial mu anti-symmetrized acting on phi, and then this guy was a plus, that was a minus, so you'll be a minus x mu eta mu lambda L. Okay, equals to 0. Okay. Now, so there I go again, right? I made a mistake here again. So this is lambda, and then this is oh no, that's oh no, sorry, this is correct. That is correct. So if you compare what we have over there to what we have over here, let me call this guy d lambda n lambda mu. 0. N, what is N lambda mu mu? You will discover that it's actually very similar to this guy. So I am going to move the index up, call it alpha, and then this will become eta mu alpha. Okay. Then what you notice is that if I bring that result over here, this is going to be, let me make all the indices the same, okay, so that we can compare. Yeah, let me do this. Let's call this lambda. So this will be lambda. And this will be lambda. Alpha, lambda. Alpha, yeah. Okay. Then this is in fact, let me just write it out first. dl d lambda phi. And then we have this anti-symmetric orbital. This is basically orbital angular momentum acting on the fields minus x mu eta mu lambda L. So if you compare this guy and this guy, what do you have? This is in fact x mu j x j lambda and then mu x mu. Okay. It's symmetric. You notice it's going to be symmetric anyway. So so in fact I can write it in either x. This will turn out to be x mu j mu alpha lambda. Getting the lambda index mixed up. Lambda. Okay. So this is the Noether current from translations. This is the Noether for Lorentz. From Lorentz. And in particular, there are at least two things I want to say about it. Okay, the first thing is that I just mentioned that this is symmetric. How do you see that? You can see it in a general way. Whenever you can get your Noether current of Lorentz transformations to be this form. In other words, whenever you can get the Lorentz, the Noether current from Lorentz to be the anti-symmetric combination of x, the Cartesian x, with the Noether current from translations, you can show that this has to be symmetric. Why? Because let's do the calculation. So you get d lambda m lambda mu has to be equal to 0. But now what does that give you? You get d lambda x. Let's use this one. J lambda mu x mu equals to 0. So when I add d lambda on j, that is conserved. This is 0. So this, because it's conserved from translations, you know it's conserved. But then there are now other terms. There's now j lambda mu, and then you're going to differentiate x, so you get Kronecker mu lambda equals to 0. So this is 0, But this guy tells you what? This is J nu mu. And because of the anti-symmetric, that means that I have to take J and anti-symmetrize the indices. And it tells me that, in fact, you're guaranteed, if you can get your Noether current from Lorentz to be the anti-symmetric combination of X and the Noether current from translation, you are guaranteed that J will therefore be symmetric. Okay. And in fact, symmetry is one criteria for this guy to be called the stress energy of matter, of whatever substance, whatever field theory you're considering. That's a necessary condition. Okay? You have to, so J mu nu equals to J nu mu, symmetry is an important feature of the stress energy tensor. In other words, if you do not find this Noether current, the one from translation, if you find that that is not symmetric, then you cannot call it the stress energy of matter. Right? And this is what we're going to see later on when we do electromagnetism. There's a problem that if you do it in a particular way, you will find that you do not get a symmetric stress tensor. And in that situation, you're not allowed to call it stress energy. I'll explain why symmetry is important. But that's the first thing I want to say. That if you find that your Noether from Lorentz involves the Noether from translation, then you can make this statement. If not, you cannot make that statement. Okay? So that's the first thing. The second thing is, what does that mean on its own? What does this guy mean? This, in fact, itself also means orbital angular momentum. So this guy, let me just write down, if symmetric, J is the energy momentum tensor. Okay, I'll say a bit more about this. But if this is related to this guy, and if this is symmetric, so if J is symmetric, then M is actually angular momentum. The most familiar example is, remember angular momentum goes like R cross P, right? It's a cross product between displacement and momentum. So let's see that this actually happens here. So R cross momentum, basically if you look at the components, itself will go like Ri Pj, and you anti-symmetrize the components. This is the dual formulation of this guy, right? This will require a Babichirita, but if you look at it component by component, basically you're looking at Ripj minus Pirj. And let's see that this actually happens, right? Just look at the, basically just look at the situation where nu and mu are spatial and lambda is 0. So set lambda to be 0 and set mu to be, say, ij. So what do we have? Then M0 ij goes like x I j 0 minus x j I 0. Now, if you believe what I just said, so this is the part I haven't proven yet, but if you believe that this is, if this is symmetric, this is the stress energy, then Pj J0 is in fact the linear momentum. This is the J component of linear momentum. Okay. Which means basically Ji0 is in fact just Pi, momentum density. So this is in fact Xi Pj, anti-symmetries. Okay. So that's how you see that, and that this is related to angular momentum. This is in fact the relativistic generalization of angular momentum, because this definition that we learned from classical mechanics is non-relativistic, right? It only involves space. If you want something to be relativistic, you need to generalize it to space and time. You need Lorentz indices, and that's what's happening here. Right? This is the relativistic version of angular momentum, and I'm just showing you that you can recover a subset of these components. In fact, give you just a regular R cross P. Okay. So after the break, I think we should take a break. After the break, let me explain to you where this interpretation comes from before we move on to do photons. Okay, so this is scalars. It's the simplest example, and especially for those who have taken GR, you will recognize right away this is in fact the stress energy tensor. But the question is, how do you arrive at such an interpretation? In GR, for those of you who hasn't taken GR before, how you get this is you start from an action, the action of your scalar field theory, and you now vary the metric. Not vary the field, but you vary the metric. And you demand that, sorry, you don't have to demand that zero, but you read off the coefficient of the metric variation, and that you call the stress energy. Okay. But in that situation, the interpretation is not clear. Right? You can argue that it will be divergence free, but the interpretation of the components is not clear. Okay? And so I think that ultimately you need this Noether procedure to give meaning to the individual components of the stress tensor. But that depends on the crucial fact that it must be symmetric. Right? So the Noether procedure, the deficiency there is that it doesn't always guarantee a symmetric stress tensor. So there's a little bit of a problem there. But if you work hard enough, at least for the examples that we care about, you can get it to symmetric form. And then that lends itself to this interpretation of being the stress energy. So I'll talk more about this after the break. Any questions first?
How about lambda is spatial index for n tensor?
Yeah, so you'll get some things like time and then cross product between time, momentum, and so for example, if you want to put I, right? Then you can put 0I, for example. Yeah, so the interpretation there is a bit more tricky. But it will involve things like time, momentum, and pressure and shear as well. Yeah, let me talk about the interpretation of the components first, and then you can decipher it more easily. Yeah. Okay, let's take a 10-minute break and we'll be back. So this is something that is very puzzling to me, but anyway, I just want to highlight this. If you look at several books and they don't care about the Jacobian, right? So somehow they don't explain why, and I think, unfortunately, I think it's wrong. So let's do it. Let's do it properly and see what we get. So essentially, you define a new variable. This is x prime of alpha. So when you want to do d alpha, and you're going to replace with d alpha prime. This is of course just dx beta, dx prime alpha, d beta. This is with respect to x, right? But this guy in turn is of course just dx prime alpha, dx prime dx inverse, right? And then you contract it with this d beta. So this is d beta alpha, okay? And what does it look like? We know that dx prime dx, let's do lambda rho, is equals to d rho acting on lambda, say sigma tau x tau, and this is Kronecker. This acting on this is a constant, so this acting on this gives you Kronecker tau rho, and Kronecker tau rho will give you lambda sigma rho. Okay. And so in particular, this will give you sigma rho minus I omega j hat mu sigma rho plus higher order terms. So the inverse of this, because it's small, this is I minus something small, identity minus something small. So the inverse is just going to be the identity plus the same thing. Okay, you can try this out. It's always going to be like that. If you multiply this to this, just a matrix multiplication, you will find that at first order, this will just cancel out exactly because this is a minus and that's a plus. Okay, and so therefore, d alpha will just simply be replaced with d alpha plus I omega j hat mu rho sigma alpha d sigma. Okay. That's all I have done is just contract this guy with this guy, right? Maybe this. So let me just write this. This is the infinitesimal version of lambda inverse sigma rho sigma alpha d sigma. Okay. And so that means the following. So remember d alpha prime, phi prime of x. By phi prime, I just mean, oops, I'm sorry, phi prime of x prime. I just mean phi, I don't mean a derivative, I just mean phi in the new coordinate system x prime. This is dx beta, dx prime alpha, d beta. This is exactly what we have just worked out. But now the derivative is evaluated at x. With its definition replaced by x prime, however you define this. Okay, that's what we mean by this. So therefore, when we have the alpha phi, it's going to be replaced with this new guy, and this is going to be simply the new derivative, which is what we have here, d alpha of phi. But phi is now not just x alone, but x replaced with a new definition, so it will be x plus, x minus I omega j hat mu. and then dotted into x. Okay. I just suppress the indices because there are too many indices. And then let's remember our Jacobian minus I omega j hat mu nu sigma alpha partial sigma phi. And here I also should write down x minus this stuff, but this is already first order. Okay, and because it's already first order, I'm just going to write down x. Because I just want to keep everything to first order. And for this guy, this is a derivative evaluated at this quantity. So I just need to also Taylor expand this derivative. Right? So let me just write this down here. D alpha of phi is now replaced with d alpha phi, and then plus the Taylor expansion of this to first order minus I omega j hat mu nu sigma alpha d sigma phi, and then plus I omega j hat mu nu sigma alpha d sigma phi of x. Okay, so now everybody is all the derivatives are evaluated at x. So simply put, the derivative of a scalar field will transform both under transformation, Lorentz transformation, both the derivative has to transform and the argument has to transform. Right? So the argument gives you a Taylor expansion of this form, and the derivative also has to transform. I'm sorry, there's a d alpha here, right? So that's one we have. So d alpha phi. Okay, so that's what, let me just say that again. This is the Taylor expansion of the derivative, whereas this is the Jacobian that comes, the infinitesimal part of the Jacobian that changes the derivative just slightly when you do a Lorentz transformation. Okay.
The second line, we consider partial x prime lambda partial x rho.
Second line, this one.
Yes.
Yeah.
Why we have the index sigma in the next column?
Oh, I'm sorry. Thank you. Lambda. Thank you. Lambda. And so this will be lambda. Thank you. It should match up on both sides, right? Yeah. So this is okay. Yeah. But if you want, I can change it just to make sure that this is okay. But let me just change it. Yep. Any other comments, questions? Let me write this properly. Okay. This is the Taylor expansion of the derivative d alpha d rho d sigma. Yeah. Okay. So we know how the derivative, derivative transforms, and of course phi itself also has to transform like this, but that's easier, right? So phi would transform as phi minus I omega j hat mu nu, and then it would be sigma rho x rho yes, I'm very, very bad here. So let me correct myself. So I forgot my x here, right? So that's what happens when you forget your indices and then you forget about the x. You get more and more mistakes. So again, this is Taylor expansion of this, so it will be minus I omega j hat mu nu sigma rho x rho. There's an x contracted with this j hat, and then this index is contracted with the derivative. And then there's already a derivative here, so there must be a d alpha phi. Okay? And then I have to remember this guy, which I shouldn't have erased, but plus I omega j hat mu nu. And this is okay because this is just a Jacobian associated with the derivative. Okay? Everybody is an x. And this would just be d sigma phi. Okay? Remember, this is all I'm doing here is I am replacing it with phi of x minus I omega j hat mu nu contracted into x. Okay? That's what's happening here. And just take x manually. So now that we know how the phi and its derivative transform, we can now come over here and combine this result together with how this guy would transform this at the level of the fields. Okay, so let me do that. Let me erase this. And then I'm going to erase that and everything above it. And then I don't really need this. I just need to record this result and this result. Okay, so I can erase everything above here. Now let's see what happens. So this is one version of delta L replaced with L plus delta L. Okay. And remember, we know how it transforms because it's a scalar. And so it's a reflection. This reflects the fact that this is space-time symmetric. And because the space-time is symmetric, also when we do a Lorentz transformation as well as the translation, the space-time transformations act only on the fields, right? There's no other factors in the Lagrangian that depends on space-time. Actually, that's a crucial point. That's how we know it's symmetric under space-time transformation. Right? The only effect translations and Lorentz transformations have are on the fields. So let's do it. So delta L is now dl d5 dd5, which I'm going to call d mu phi, and then it's going to be delta of d5. But what is delta of d5? We just figured out is this whole thing here. Okay, this is why I first worked out the transformation in the field and its derivative so that I can work it out. I can just plug it in. So therefore I can just stretch this out and just replace it with this whole thing here. So I get, I'm going to pull out minus I omega. In fact, I'm going to do this away. I'm going to pull out omega, and then I have I minus I j hat mu nu, and then sigma rho x rho d sigma d alpha I I'm sorry, this alpha is this alpha, which I'm now calling mu, so this should be called mu phi. And then this alpha will be mu, so it'll be plus omega, I put it out already, so it's I j hat mu sigma mu, and then the sigma phi. So I know it's a little messy, but this is delta phi, delta of partial mu phi, okay, which is this guy here, and then plus the mu, dl, d phi, and then delta phi. But what is delta phi? Delta phi is exactly this piece. Okay, this is phi going to phi plus delta phi. So I'm going to take this guy and plug it in here, and that will be, in fact, just a Taylor expansion. So it will be omega times minus I j hat mu, and then it would be sigma rho x rho d sigma phi. Okay? And then this is delta phi. What I'm going to try to do is to integrate by parts this fellow over here. Okay. And so this is the part where it's a little tricky. So when you integrate by parts, strictly speaking, you need to act on this as well. Okay, so let me just write down. So this is now dl d. Let me write it down. So dl d phi minus du dl du phi, and then it's multiplied by d phi, so I have an omega, and then minus I j hat mu sigma rho x rho d mu d sigma phi. Okay? And so to cancel this term, I don't really have this term. So to cancel this term, I have to add the total derivative like that. It's going to take the divergence of dl d mu phi, and then this guy here, omega minus I j hat mu sigma rho x rho d sigma phi. Okay. So when when I act this on this, it will cancel out. But when I act this on this guy, I get this, but there's an extra term, okay, which I need to cancel out. So I need to cancel out also the term acting on this. Okay, so that would be actually minus dl d mu phi omega minus I j hat mu sigma rho, and then when I take the derivative mu acting on x rho, this would give me Symmetric rho mu. Symmetric rho mu, yes, and then d sigma phi. Okay. And then let me not forget this term. There's also this term here, which is plus dl d phi, and then omega j hat mu sigma mu d sigma phi. Okay. Yeah, so you see what happens is that, in fact, I have a plus here. Okay, so what you end up with is that this becomes, so this term here is in fact, so I'm going to just put a plus here. This term in fact becomes I j hat mu, and then becomes sigma mu d sigma phi, which is of course nothing but this guy as well, right? So therefore it becomes twice. You can combine them. So this is the point where we appear to get stuck, because Noether's theorem tells us that we should get a conservation law, which means that we get a divergence of a current. Okay? We should get a divergence of a current, and it should all be zero. But what happens is that, thankfully, because this theory is Lorentz invariant, we need to make a further argument. So I'm going to erase this, and I'm running out of space. So because the theory is Lorentz invariant, and we're only talking about one real scalar field, actually the Lagrangian must only depend on the kinetic term and phi. Okay, so this is actually the only way we can find invariance. So why? Because Lagrangian is invariant. So therefore it must depend on scalars. Because if the Lagrangian is a scalar, how can you have a freestanding vector or tensor? You cannot have a freestanding scalar or tensor. So you must build the Lagrangian out of scalar things. So how do you get a scalar from taking the gradient of phi? You have to dot it with itself. Right? And of course, phi is scalar in itself. So what you recognize is the following. If you recognize this, then dl d mu phi is in fact always going to be the derivative of L with respect to the kinetic energy, and then multiplied by the derivative of this. So in fact, it will be twice of d mu phi. This is always going to happen. Okay? And once you recognize that, then we can see what happens to this term. And it turns out that it will drop out because of that, and exactly because the Lorentz generator is anti-symmetric. Okay, so let's see that explicitly. So what do we have over there? We have the contraction with I j hat mu, and then sigma mu d sigma phi. Okay? And what we've just shown is that this is going to be dl d phi squared, and then there's going to be a 2i, and then there's going to be a d mu phi. Nobody stopped me, right? I shouldn't be using mu because I have a mu nu. I'm going to use lambda. sigma lambda d sigma phi. So remember that this is anti-symmetric. In particular, if I pull out a minus sign, if you guys remember, because it's a generator of Lorentz transformations, minus I times this guy, in fact, let's write it with both upper indices, or let's do this, lambda, sigma, sigma, okay? And it's easier to write it as an anti-symmetric form. Then with a minus sign, you will get, in fact, the following. You get Kronecker nu, sigma, lambda, and then you anti-symmetrize these guys. And because it's anti-symmetric and you have just two scalar fields, these guys are symmetric. Rho, sigma, the gradient with respect to rho, lambda, and the gradient with respect to sigma, you can just swap them all in one, is symmetric. So in fact, this is zero. Okay? This is zero. And therefore, this is zero. Okay? I'm very sorry, but I use mu, right? So I will have to change this to lambda. Lambda. This is lambda. This is lambda. No more lambda. This is lambda. This is lambda. This is lambda. Because my mu is fixed, right? So I have to use a different symbol. Okay. So what I've shown is that this guy, which is equal to this guy, they are both zero. Okay? They are equal, and because they are equal to this, and by Lorentz invariance, you can show that it always cancel out. It will always cancel out. And therefore, what do we have right now? We have delta L from varying the fields, and this makes use of the Lorentz invariance of the action. We have gotten it into an Euler-Lagrange form contracted with delta phi plus the total divergence of this quantity over here. But of course, we also have delta L from this Taylor expansion. Right? And therefore this must be equal to this. And if we use the equations of motion, then let's summarize what we have over here. I'm sorry, I don't know more space, so I have to erase the stuff here. And since this is zero, I can erase it too. Okay, so what do we have here? Delta L, so using the equations of motion, meaning dL d phi is equal to d lambda dL d lambda phi. And this first term will cancel out, and let me drop the omega on both sides. So I have d lambda acting on dL d lambda phi, and then minus I j hat mu sigma rho dx rho